Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So today we will be doing more of algorithms of finding the greatest common divisor or highest common factor, the HCF or GCD. So today's contents will be first be revisiting the naive algorithm for finding the GCD, and this is something that we have done last lecture. We will be revisiting it again. Then we will be going to better algorithms for GCD. At the end we will see some ideas about how that better algorithm can be made even better. Okay. So let us start with the goal that we have in hand, which is we have been given two positive integers p and q, and we want to find the greatest common divisor of p and q. So greatest common divisor, also known as highest common factor, HCF, it is the largest integer that divides both the given integers p and q. So for example, if p is 14 and q is 8, then the highest common factor of GCD, greatest common divisor, is 2, which is the largest integer that divides both of them. Similarly, the GCD of 12 and 18 is 6. Note that something less than 6 can also divide. For example, 3 divides 12 and 18 both, but since 6 is the greatest common is larger than 3, so 6 is the greatest common divisor. Note that no other number greater than 6 divides both 12 and 18. The goal is that we have been given two integers p and q, and we want to find the GCD of these numbers. In the last lecture we saw the most basic algorithm, or which we can call the exhaustive search algorithm. So we will just revisit it again. So what do we do? So for example, if we want to compute the GCD of two numbers 12 and 18, we know that a GCD, since it has to divide both 12 and 18, it better be less than 12, otherwise it will not divide 12. So we write down in a array the numbers 1 to 12, all the possible integers that can be a divisor, and then what we do? We go one by one from left to right and try to mark out which all integers divides both 12 and 18. For example, let us say 1, yes, 1 does divide 12 and 18, so we mark it color red. Then comes 2, yeah, 2 also divides 12 and 18, so we mark it colored red. Then come to 3, again 3 divides both 12 and 18, so we mark it colored red. Then we come to 4, 4 does divide 12 but does not divide 18, so it cannot be a GCD, and hence we leave it as black. Similarly for 5, and when we come to 6, we see that 6 divides 12 and 18, so we mark it as red because that is a possible GCD. And then you can verify that all the other numbers will either divide 18, either not divide 18 or not divide 12 or both, so they are not possible GCDs. Thus we have this array with some of them marked red, and the next thing we do is we go from right to left and find out the first number that we encounter, which is red, which is in this case is 6, and that is the GCD. This is a nice exhaustive search, and we have done this pseudocode for this algorithm last class, which is we have this array A which has p point places. Initially all of them are black, and if a particular I divides both p and q, we mark it as red. And once that is done, this for loop, which is basically the loop that marks red or black, we go from right to left, that's from p to 1, and we output the first integer that is marked red. This is exactly the kind of algorithm that we expect to see. In the last lecture we had done a more exhaustive understanding of this particular algorithm, and what we found out was this algorithm does compute the GCD of two numbers correctly. We also proved that the time complexity is basically the number of steps required. In this case it will be something like 4p, where p is that first integer for which we are finding the GCD. Now, since the given input is a binary representation of the integers p and a binary representation of the integers q, so the length of the input or the input size is log p to the base 2 plus log q to the base 2. So, the input size is of the order of log p to the base 2, whereas the time complexity or the number of steps of the order of 4p. So, 4p is exponentially log p to the base 2, thus the time complexity is exponential in the size of the first input. The space complexity is the number of places that we need to store. In this case we had to store the array, whole array which had p elements, the array A that had the p elements there, and thus the space complexity was also p, which is again exponential in the size of the first input. Now we come to the next important question, that is this algorithm the best one can hope for? And the answer is yeah, we can make much better. So, let us start with another algorithm which can help us to make it better. This improvement is much more of a implementation level, as we will soon see it. So, let us see the idea of the improved algorithm. For example, let us take our favorite numbers, p is 12 and q is 18, and if you want to compute the GCD of 12 and 18, we first, as we have done in the earlier basic algorithm, write down the numbers from 1 to 12. Okay. And now, instead of writing it in an array and storing all the bits as red and black, instead we have some value called temp. Temp is some kind of a variable that is still unmarked, a single bit variable. Okay. Now, let us start from the left to right. So, we first go to 1 and we find that 1 is something that does divide 12 and 18, that is in our earlier case we would have marked it red. Here also I just show it as marked as red, but we need not do it. Instead we change this temp from temp, we assign the value 1. Then we go to the next value 2 and we see that the 2 again divides 12 and 18. So, that is it's again a candidate GCD, and we mark that one red in the basic case, and here we update this value temp from 1 to 2. Again we go to 3 and we see that 3 divides both 12 and 18, and again we update the value to 3. 4 does not divide 18, it does divide 12, thus it is not a possible value for GCD, hence we would have left it as colored black. In this case we leave our variable temp as it is, which is 3. Similarly for 5, and then we go to 6 and we see that 6 divides both of them, and again we update our variables to 6, and for the rest of the numbers we go one by one and find out that none of the numbers divide both 12 and 18, and thus we do not update our value temp. At the end, instead of having an array of red and black as we would have got in the case of the first algorithm, we have just one value that contains our value GCD. So, at the end of the algorithm we can say, oh, GCD of 12 and 18 is 6. Now, this is a simple algorithm and the pseudocode of this is also very simple. First, we initialize a variable temp and we have not put any value to this value temp now. And then as we move from 1 to p, from left to right, if we find I divides p and q, we update the value of temp to I. And after this whole of the for loop is finished, so the temp now contains a particular value and we would output that particular value temp. This again sounds like a very simple algorithm, and it is in fact an obvious algorithm. So, let us see what all things that we need to do here now. As we have discussed in last lecture also, once you have the pseudocode, we have to prove that the algorithm terminates, we have to prove that algorithm outputs the correct value of GCD of p and q, and we have to check the time complexity and the space complexity of this algorithm. So, let us start with this the first thing to prove that the algorithm terminates, and again here it is not very hard to see that the algorithm terminates. First of all, here the for loop takes exactly p rounds, and in each round there is only 2 steps that it does. So, for the for loop it does 2p steps, and thus the algorithm overall with the initialize and the output ends up taking 2p plus 2 step. It is of course better than, if you remember, the basic algorithm where the number of steps of the algorithm was the order of 4p plus 2, and here it is 2p plus 2. So, thus we get a double the speed in some sense, but that is not something we are that much concerned about, a constant factor improvement. We are usually more interested in much better improvement. Now, let us go to the correctness of this algorithm. Again, the correctness is almost obvious. Note that since the temp always divides p and q, whatever you output the temp finally, that is something that was updated to I if and only if I divided both p and q. Thus, whatever the output is always divides both p and q, and let the GCD of p and q be actually be x. So, if x is bigger than what we output finally, then when we had gone from 1 to pth round of the loop, we would have updated temp to x, but that did not happen. Thus, GCD of p and q cannot be strictly greater than the output. So, we have that the output is something that divides both p and q, and no other element, or rather the GCD cannot be bigger than the output. So, GCD must be equal to the output. So, this gives us the correctness of the next comes the time complexity of this algorithm, and it is exactly same as the proof of termination, which is again that this loop takes 2p steps, and thus the time complexity is 2p plus 2 steps. Again remember that p is exponential in log p to the base 2, which is the size of the input, and thus the runtime or the time complexity is exponential in the input size. We will take a short break now and we will come back and do the rest of the lecture. Thank you. Welcome back after the break. We were doing the algorithms for finding the GCD of two numbers p and q, and we had seen a basic algorithm earlier, and then we were seeing this better algorithm, which is the one that you can see on your left hand side, and we had just finished analyzing the time complexity of this algorithm. The time complexity was exponential in the input size, which was also the case in the basic algorithm. So, in some sense one can say it is not much improvement than the basic algorithm. The main improvement comes in the space complexity. Note that in the earlier algorithm or the basic algorithm, we had to store the whole array A, which had p entries. Thus, the space complexity there was p, whereas here in the for loop we do not store anything. All that we store is this, initialize this variable temp, and that is the only thing that we are storing. Thus, the total space complexity is amount of space required to store temp, which is a single bit variable, and possibly some other registers like I and all, and we call this one. So, the space complexity is constant. So, this is where we make the significant improvement over the earlier basic algorithm. This better algorithm does compute the GCD of two numbers. The space complexity is exponential in the first input, which is not any improvement than the earlier algorithm, and the space complexity is constant. So, in comparison to the basic algorithm and this current better algorithm, we have a time complexity that remains same basically. Again, I am not distinguishing between 2p and 4p, I am distinguishing more at this level of whether it is exponential or linear or what. And the space complexity in the earlier one was also exponential in the first input size of the first input. In this case we have constant. So, thus here we have an algorithm that is significantly better, at least in terms of the space complexity, than the earlier algorithm. Note that this algorithm did not do anything much innovative or new as such. This improvement came more from an implementation level. It is just under the understanding or realization that in the basic algorithm we were storing this array, which is not necessary. All we needed is to keep the highest value, which divides both p and q, and what it did for the better algorithm. Clever implementation can improve the complexity, time complexity or space complexity of various algorithms. Now, the question is, can we do even better? And the answer is yes again, but this time to make the next big step we would need to have something more trick or more a new idea instead of just a new implementation improvement. So, let us see. To understand this new trick, we have to revisit our understanding of the GCD itself. So, in the earlier lecture we had talked about the properties of GCD. Most of them are obvious. For example, the GCD of p and q was equal to GCD of q and p, right. If a number divides both p and q, then it also divides q and p. The ordering of p and q does not matter, it is obvious. The second one is, if p divides q, then GCD of p and q is p, because of course p divides p and q. So, p divides p, p divides q, and no other number greater than p can divide p. So, GCD cannot be bigger than p. So, the GCD of p and q in this case has to be p. And the third one, which was the more interesting one, that if some other number divides both p and q, then this number t divides the GCD of p and q. This possibly can require a little small proof. We had seen this one in the last lecture. I will not go into details of this particular proof right now, but here it comes the understanding, the need to understand GCD better. There is one more trick that we can apply, and this is a trick we have not seen earlier, which is that if I write say p, so or rather q as some integer d times p plus r. So in other words, you can think that I divide q by p, d is the quotient, so that this is what is the answer I get after dividing it, and r is the remainder. Then GCD of p and q is equals to GCD of r and p. This particular property is not obvious, and we need a proof for that, and we will then see how this particular property can help us in getting towards a better algorithm. So here we have the proof for this property 4 of GCD, which says that if we write q as some integer times p plus a value r, then GCD is of p and q is equals to GCD of r and p. So let us first assume that this GCD of p and q is some value k. Now by the definition, k divides both p and q. K divides both p and q, then k must divide q minus dp, because note, k divides q, k divides p, and d is an integer. So k divides dp, k divides q, so difference of these two also must be divisible by k. So thus k divides this whole number q minus dp, which in our case is equals to r. Q minus dp equals to r, right. If k, thus k divides GCD of r and p, because k divides p, and that was something that we had seen from the definition of k, which was the GCD of p and q, and k divides r, and thus k divides GCD of r and p. This was the third property of GCD that we had written up. Here we have that if GCD of p and q is k, then k divides GCD of r and p. Now comes the other direction, that if GCD of r and p is equals to L, then what do we know? L divides r and L divides p, and again by the similar logic, L must divide the linear combination of both of them, which is dp plus r, because L divides p, so L divides dp, and L also divides r, so L must divide the summation of those two. And so again, as we had seen earlier, L divides p is something that we have, and L divides q, that is something that we have here. So L divides both p and q, and thus L divides the GCD of p and q. So we have, if GCD of p and q is k, then k divides GCD of r and p. If GCD of r and p is L, then L divides GCD of p and q. And now if a divides b and b divides a, then since a and b are integers, we do get a is equal to b. Thus we have these two are equal. So this is the proof of the fourth property that we have. So thus we have this 4 properties of GCD. We have added a new property just now, which is this. Now comes the next point. Can we use this particular property to get some slightly better algorithm? Here is the idea. By the fourth property, we know that if you can write p as dp plus r, imagine here that r is the remainder when you divide q by p, then GCD of p and q is equal to GCD of r and p. So we can use that idea. Say for example, we want to compute the GCD of 12 and 44. What do we do? Just like q equals to dp plus r, we write 44 equals to 12 into 3 plus 8. We have also written 12 into 2 plus 20. That also would have been fine, but we can also write it like this. How we choose this r is up to in our hands, and the smaller we choose, better it will be. So we write 44 equals to 12 into 3 plus 8, and then by this property, we know that GCD of 12 and 44 is equal to GCD of 8 and 12. Already you can see a marked difference. The numbers are going down, and this is exactly where we want to make our advantage. Again, similarly, we can write 12 as 8 into 1 plus 4, and by the property we know the GCD of 8 and 12 is equal to GCD of 4 and 8. And then finally we see that 4 divides 8, thus 4 must be the GCD of 4 and 8, which must be the GCD of 8 and 12, which must be the GCD of then 12 and 44. Similarly, we can do a similar one more example, that say GCD of 14 and 33. 33 is 14 into 2 plus 5, and again 14 is 5 into 2 plus 4, and similarly for 5, and thus since 1 divides 4, so 1 is the GCD of 1 and 4, which is the GCD of 4 and 5, which is the GCD of 5 and 14, which is the GCD of 14 and 33. So this is the idea. Stop this lecture at this step. We will come back next lecture to understand this particular algorithm. In this lecture we did this first the basic algorithm, and then we went to a better algorithm for GCD, and then we saw a property that can be used for obtaining a new lecture. In the meantime, I would like to leave you guys with some questions. Use this particular idea to design a new algorithm. Write down the pseudocode of this algorithm and try to convince yourself, is this algorithm really better than the earlier two algorithms that we have seen, and if so, let us try to prove that. So with this we come to the end of this episode. In the following episode we will analyze this particular algorithm, the new algorithm, and we will see whether this algorithm is indeed better than the earlier two algorithms or not. Thank you.